All right, so we continue on the topic of relaxed memory models. And in presence of many existing hardware architectures and many possible optimizations that the compilers might do, the question of which optimizations can be applied to which models becomes particularly acute. And now John is going to tell us how to answer this question with the support of an automated tool. So please.
Hello, my name is John Wickerson. This is joint work with Mark Batty, Tyler Sorensen, and George Constantinides. Is that better? So, modern multiprocessors like x86, ARM, and Power, graphics processors like those by AMD or NVIDIA, and concurrent languages like C, C++, Java, OpenCL, they all allow certain memory accesses to occur out of order. And exactly which memory accesses are allowed to occur out of order is defined by the languages or the architecture's memory model. To give a quick example, this program has two shared locations X and Y and two registers R0 and R1. And if you run this program under the sequential consistency SC memory model, then there are three possible outcomes. And they correspond to whether the threads are interleaved like this, or like this, or like this. But if you run the program according to the x86 memory model, then there's one extra outcome that you could occasionally observe, where both registers end up with 0. Quite why this happens is because of some fancy architecture optimization to do with write buffers that delays the propagation of writes from one thread to the other. So this program is interesting because it is able to distinguish one memory model, SC, from another, x86. And in general, this work is all about how to compare two arbitrary given memory models. So the problem that we tackle is memory models are complex and they're counterintuitive. They're like this because they encompass a whole load of fancy compile optimizations and architectural optimizations that make modern computers and languages so fast. But the problem with this complexity is that it has led to a whole load of bugs in programs, in compilers, in architecture specifications, all caused by people not understanding this complexity. So in the face of complexity, what you need is tool support. So what we offer is a tool, a technique for automatically comparing two memory models. And this is useful because it means that you can take two variants of a memory model that you're developing, and you can assess by comparing them, you can assess the impact of this proposed change. And you can also use a comparison of memory models to debug compilers. And I'll say a little bit more about that now. So, in short, there are three things that you can do if you can compare memory models. First thing you can do is you can show that one memory model, say M, is stronger than, so more restrictive, allows fewer behaviors than another memory model, say N. And you can do this if you find a program P and a final state sigma, such that if you run program P according to memory model M, then sigma is not one of your possible final states. But if you run that program P on memory model N, then sigma is one of your possible final states. Second thing you can do is you can show that a compiler optimization is unsound for a language that has a memory model, say, M. And the way to do this is you find a program P and another program Q and a final state sigma, such that if you run program P under memory model M, then you can't reach final state sigma. But P optimizes to Q. And if you run Q under that same memory model, then you can reach the final state. So what's happened here is the process of doing this optimization has allowed the program for the first time to reach the outcome sigma. The optimization has introduced a new behavior. And this is exactly what compiler optimizations are not supposed to do. And thirdly, you can check compiler mappings. So suppose you have a compiler mapping from a language with memory model M to a language with memory model N. You can find a bug in that mapping if you can find a program P and a program Q and a final state sigma, such that if you run program P under the source level memory model M, you can't reach final state sigma, but nonetheless P compiles to Q, and if you run Q under the target language's memory model N, then you can reach final state sigma. So again, the process of doing the compilation has allowed the program to now reach this final state sigma. You've introduced a new behavior. This is exactly what compiler mapping are not supposed to do. These three tasks have been studied quite a bit in the literature. So the three rows here correspond to the three tasks. In the first column, I give a number of works where the authors have either compared two memory models, they've found programs that can distinguish them, or they've checked compiler optimizations, so found programs that exhibit a bug in the optimization, or they've checked compiler mappings and found a bug in the mapping. In all of these cases, it's a very difficult thing to do, from my own experience. These memory models are very complicated, and there's no particularly reliable way, other than just trial and error, to come up with these examples, and you never know you found the smallest example. On the other hand, the second column is works where they've done the opposite, so they've proved that two memory models are equivalent, or they've proved that a certain compiler optimization is sound for a memory model, or they've proved that a compiler mapping is sound. All of these proofs are laborious efforts. It's very, very difficult. And they're very fragile if anything changes. So they're really not suitable for rapid development of new memory models and new compilers. So finally, the third column, the automatically doing these tasks, at least up to a bound, I should say, is where this work fits in. And there have been some previous works in these cells. So that Manuel and authors, they have a tool for comparing memory models, but they only look at the architecture level memory models. They can't handle the software level memory models that have data races and so on. Compiler optimizations, there are tools for checking compiler optimizations, but they focus on specific instances of optimization rather than the optimization in general. And there is a tool for checking transformations between memory models, but it looks at the architecture to microarchitecture interface rather than the language to the architecture, where we focus. So I want to spend the rest of the talk explaining how we do this memory model comparison and what the challenges are. But before I do that, I want to give our results. So we gave our tool a number of challenges in these rows. The first three are comparing some recently proposed variations on C++ memory model by these three authors, comparing those against the original C++ model. And the column over here gives the size in terms of number of instructions of the program that the authors gave for distinguishing their new model from the original one. Okay, and these programs were all manually found. And this column is the size of the program that our tool automatically generated when faced with the same problem. And I've highlighted cases where the tool managed to come up with a smaller example than the experts managed to find by manual effort. And I also give an indication of how long the tool takes to do this, and you can see it's quite a bit faster than any expert could be. The second batch of results is for compiler optimizations. So we checked a few compiler optimizations for C++. Tavafiadis and colleagues had found some programs that exhibited bugs in these optimizations already. We gave the same task to our tool, and without any guidance, it was able to come up with similar programs, and in one case, it found one that was even smaller. And it's a similar story for compiler mappings. So we looked at compiling OpenCL to AMD graphics processors, and also C++ to power multiprocessors. And again, this is previous works have shown that there were bugs in these mappings, and our tool, without any guidance, was able to automatically recreate similar instances of the bug, and in one case, smaller than the manually found programs. So, to tell you a bit more about what the challenges are in comparing memory models, I need to give you a little bit of background about how memory models work. So if you return to this small example, how was it that I was able to tell you that with this program, under SC you have these outcomes, and under x86 you have these outcomes? How can you calculate this? Well, these memory models work in two phases. The first phase is to transform from the source code into a set of tracers, or execution graphs. In these execution graphs, there are a bunch of nodes, graph vertices. Write event correspond to store instructions. Read events come from load instructions. And there are various edges between the event in the execution graph. So the SB edges, that sequence before, that captures the order of the instructions in the original program. And then RF, reads from, that captures the transferal of values from write event to read events. So this read here gets a 1 because it reads from this write, which set the 1. A piece of source code will give rise to a whole bunch of these possible execution graphs. There's another one here where this read is getting a 0. It has no RF edge coming into it. And there's another possibility here, and another possibility here. And each of these execution graphs leads to one of these post conditions. The second stage of calculating the semantics is to throw a memory model at it. So with the SC memory model, SC would look at all these executions in turn, and it would say yes, 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 and no. So it spots certain patterns among the node and the relations in this graph that it doesn't like, so it says no to that one. Whereas x86 would say yes, 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 and yes. Okay. So why is this tricky? Why? So just focus on the simple case of comparing two memory models. Basically what we're asking for is find me an inhabitant of this set. I want to program P, final state sigma, such that if I run program P according to memory model M, then I can't get to sigma, but if I run it under memory model N, then I can get to sigma. So what you might try is just throw that problem at a constraint solver. And the constraint solver we use is called Alloy. And we tried this, and it didn't work. Why didn't it work? Well, the problem's rather hard. You see, what you're asking the constraint solver to do is find a program and a final state sigma such that of all of the possible executions of that program P that end up with final state sigma, so call those X, S prime, and so on, we require that all of those must be inconsistent, so not allowed according to memory model M, but at least some of them must be allowed under memory model N. And so what the shape of the problem is, show me that there exists a program P such that for all executions, property. And it exists for all. That's the tricky bit for the constraint solvers. So what we do is we say, well, let's not get the constraint solver to generate P directly. Let's ask the constraint solver to come up with X. And we'll ask it for X such that X is consistent according to memory model N, inconsistent according to memory model M, and then from this execution, we reverse engineer a litmus test, a program, working backwards. And this process of reverse engineering a litmus test out of the execution is actually very straightforward. For instance, in the execution, if you see a write event, well, then you just put down a store instruction in the program. And if you see a read event, well, that gives rise to a load instruction in the program. Straightforward process. And you constructed this program such that X is one of its executions. Okay, so we've got ourselves a P and a sigma. And it is the case that if you run P and according to memory model N, then you can get final state sigma. We know this because you can take execution X and it's consistent. So this litmus test can pass, as it were. And we know that it also can fail because it might go, according to memory model M, because it might take execution X, which is inconsistent according to memory model M. But we're worried about the fact that there might be some other execution of this program, say X prime, that also allows program P to reach final state sigma, and that execution X prime is consistent according to memory model M. Okay? So we don't know that the litmus test must fail according to memory model M. How do we get around that? Well, we impose an extra restriction on X when we generate it. We say it must be dead. The precise definition of dead is in the paper, but the effect of it is that you get guarantee that when you reverse engineer the litmus test from X, you know that the only way that litmus test can pass is by taking that execution X. So you don't have to worry about X prime. So in my final slide, I want to say a little bit more about this reverse engineering process that takes you from an execution to a litmus test. So suppose we've used Alloy, and it has come up with an execution that looks like this guy. This is a C++ execution, so I have the event tagged with these things like this is a non-atomic write, and this is a release atomic write, an acquire atomic read, a non-atomic read. What you need to know about this execution is that it's inconsistent, so it's not allowed according to C++. Okay? For those of you who know litmus tests, this is a violation of the message passing shape. And we can construct a litmus test from this execution, and it would look like this. See, the write event has become a store instruction, the read events have become load instructions. But the problem, because this litmus test is useless. It has a race. There's a data race on X between these two threads. And in C++, if a litmus test has a data race, all bets are off. Semantics can do anything. So in particular, you can't use to compare memory models. However, if Alloy had come up with this example instead, which is pretty much identical, indeed it's inconsistent for the same reason as before, but it has this control dependency, CD, between the reads. Then, when you turn that into a litmus test, you get if statement that checks that this load acquire really did happen. And that's enough to avoid the race. So this litmus test is useful. We like this one. So this is where the dead predicate comes in. We'd say this execution is bad, we don't want this one. This execution is good, so we'll say that one's dead, and we'll make sure that Alloy only generates ones like this. And the way we do it is looking for certain patterns like RF followed by a control dependency, this sort of thing. Okay, so in conclusion, we've used the Alloy constraint solver to compare various memory models and to check for compiler bugs. We've been working with several industrial partners to help develop the memory models of the future and to check their new compilers. And in other future work, we'd like to investigate how to extend our approach to handle more recent styles of model, like the very recently presented promising model. So thank you very much for your attention.
We have plenty of time for questions. Patrick?
You did not spoke about fences and how do they interfere with your presentation?
So the question was about fences. Yeah. Yes. I don't. Yeah, so we handle fences. I don't think there's anything. There's nothing specifically interesting about fences that pertains to this work, I would say. So we include them, and they do their fancy things, and everything sort of works.
In some model you might have some kind of fences, and in other one other kind, and they are not really comparable. And so you have stronger one in one, and so you eliminate behaviors that would be allowed by the other. You assume you have the same fences in the two models.
Oh, you mean when you're are you talking about when you're say you're doing one of these compilers and you're going from say C++ to Power, and you've got C++ fences and you've got Power fences, and they're sort of different. Oh yes, absolutely. So yes, I mean there are all sorts of issues with the fact that we're trying to fit all these different types of execution graph from languages and from architectures. I mean, it's all got to fit in the same framework in order that they can all encode the whole thing as into Alloy as a single SAT query. Yes, absolutely. And so yeah, I mean, to do it, I suppose it's a case of just trying to be general, have fence events. Yeah, it all just works. Sorry, yeah, but it's a good question. Yeah.
Were there any scalability issues in using the Alloy constraint solver?
Yes, I mean it's exponential. Empirically, well, so the way you use it is you specify an upper bound on how many how many events you want in the executions that you're searching for. So you start very small, and then when you don't find anything, you grow that bound until you get bored. And so in practice, a lot of memory-related bugs can be found with really small examples. So you're lucky like that. Occasionally, you have to go pretty big. So one of the examples required a single litmus test with 12 events, which is pretty huge. And luckily, Alloy was able to find that. But yeah, we're very much, that's about the limit, I would say. So.
Okay.